Hello, everybody. Welcome to today's lecture. So today we're gonna finish up chapter 2. We just have to talk about 2.7, but it is a little bit on the longer side. But it still probably won't take like a full hour. Um, so this is the last section of descriptive statistics. So these are the types of statistics where we're just merely describing the data. We're not making any conclusions based on the data or anything like that, right? Like when we were talking about measures of the center, like average, median, mean, mode, we're merely describing what's happening with the data, right? We're not saying because the mean is this happens, or, if the mean is below 10, then this happens. We're not making any conclusions about it. We're merely describing it. In the later chapters, we're going to use these descriptions to make conclusions, but we haven't gotten there yet. Before we do, we need to talk about probability, because when we're talking about statistics, we're typically, I shouldn't even say typically, we're never really saying anything is 100% true, because we're working with samples and we're using that to predict populations, right? Or statistics to predict parameters. So since we're never saying anything is really 100% true, we need to discuss probability so we can say, okay, what percentage can we be certain to, right? Like, is it 95? Are we 95% sure that it's true? Are we only 50% sure that it's true? Because that's clearly going to be a big difference with how much stock we should put into it, right? So that's what the next 3 chapters are going to be. We're going to talk about 3 a lot, but then 4 and 5 we're just going to kind of breeze over. One thing that we haven't really talked about, maybe I should have mentioned this in chapter 1, but when we're talking about statistics in particular, we're typically doing what's called inductive reasoning, right? Which means we take something small and we predict something large. This is inductive reasoning. We are it's the opposite of deductive reasoning, where with deductive reasoning we start with something more general and we make particular conclusions about it. Okay. So this is inductive. So most of math would fall under deductive reasoning, and like logic, philosophy, critical thinking, a lot of it falls under deductive reasoning. When you're talking about like logical fallacies and stuff like that and how to make a proper argument in a critical thinking class, that's typically deductive reasoning. Inductive reasoning is it's not the preferred way of reasoning because you can't be 100% sure, right? If you do deductive reasoning properly, you're always 100% sure, whereas with inductive reasoning, you can't be 100% sure because you're taking specific examples and trying to generalize them, which can go wrong, right? So this is kind of like the theme we're working with, which is why we need to talk about probability next before we can dive into inferential statistics, where we're actually taking our data and making conclusions. Maybe I'll talk some more about that at the beginning or end of the probability discussion. For now, for 2.7, we're still talking about descriptive statistics. So here we're not even making any conclusions, so we're not even really doing any kind of reasoning. We're merely just describing the data. So far we've talked about the measures of the location of the data. So that was like the quartiles and the percentiles. And we talked about the measures of the center of the data, like average, mean, median, mode. Now we want to talk about the measures of the spread of the data. Okay, so if we know where the center is and we know generally where the data is located, that's great. But oftentimes we want to know, okay, in general, how far spread out is your data, right? Like, is it all concentrated around the center? Is it all, like, does it look more like this, right? Where everything's concentrated around the center? Is it more like this, where you have a lot of data on either extreme and then like nothing in the middle? So we're going to start talking about the spread, and we're going to define some terms that maybe you've heard before, but maybe never really knew what they were. At least that's how I was when I first started looking at this stuff. It's like I had heard these words before a lot, but I never really knew what they were. So, the first one is going to be the standard deviation of the data. Okay. So, standard deviation of the data. So, standard deviation, this is one of the words that maybe you've heard it before, but maybe you didn't know what it was, or maybe you do. Let's think about what these words mean. Well, deviation, that means how far away is something, right? Like if you're talking about how much does something deviate, you mean how far away is it from everything else? So that's typically what we're talking about here. But that word standard, it puts a little bit of a spin on it. We're going to take the deviations of the data and we're going to do what's called standardizing them. Okay. And that's something we'll commonly do in statistics. It'll make more sense when we talk about the actual formula of it. But first, let's talk about the definitions of it. Okay. So the definition here of standard deviation, which we'll abbreviate just as SD. Okay. The standard deviation is a number that measures how far data values are from their mean. Okay. So we're measuring how far data values are from their mean. So just with the deviation part of it, we're typically taking the difference of the data value and the mean, and that tells you how far away it is. That's what the deviation would be. And then the standard deviation is going to standardize it a little bit so that it works for all of the data, right? So the process is going to be finding all of the deviations and then basically adding them up. We're also going to have to square it and take a square root, but we'll explain that when we get there. So some key things about the standard deviation. One, we're measuring how far away they are. Typically, when we measure distance, it's always positive, right? If you're talking about distance and other types of math, you're usually talking about like the absolute value. Or if you think about like the Pythagorean theorem, right? When you're trying to find the distance of, which is the length of the triangle, your numbers are always positive, right? So same thing here. We're going to make sure in our formula that the numbers will always come out positive. We're going to kind of force them to come out positive. We're actually going to use basically what is the distance formula from college algebra, if you've taken that class. Let's see. Let's take a look at how we get the equations here. First, as a reminder, because we're going to be using this a lot, reminder of the notation, the sample mean is x bar, okay, x with a bar over it. The population mean is mu. This is the Greek letter mu. Okay. So these are going to be in the formula. So just as a reminder of what these are. So first, let's look at calculating this. Okay. So a deviation, first of all, like I said, if we're talking about the deviation, how far away something is, well, let's think of like a number line, right? And we have 1, 2, 3, 4, 5. And we have 5 and we have 2. If we want to know how far apart these are, what we do is we just take one of them and subtract off the other one. And, you know, if we did 2 minus 5, we'd get the same thing except for it would be negative. So instead, to make sure it's not negative, what we do is we throw these bars around it, which means the absolute value, which just means make whatever's inside of it positive, right? But let's just worry about the difference part first. To find the distance between two things, we're just taking the difference. We're subtracting them. So the difference between the distance between 5 and 2 is 3, right? Because that's what their difference is. That's all we're going to do here. If we want to find the deviation for a data value, it's going to be equal to the data value here, let me write it on the next line. The data value minus the mean. Okay. In other words, x minus x bar. Okay. And if we're indexing our data, remember if we're like putting in order, like x1, x2, x3, then it would be like whatever your xi is, whatever place value you're in. So maybe x1 minus x bar is the deviation for the first data value, aka how far away it is from the mean. X2 minus x bar is how far away the next one is, so on and so forth. Let's use some actual data so we can kind of see what is happening here. And notice this is only the deviation, not the standard deviation. So let's use some more quiz scores here. Or test scores, rather. I don't remember exactly what they were last time, so I'll just go ahead and make up some new ones. One, two, three, four, five, six, 7. Okay. So let's say these are the test scores. So if we wanted to index this data, like if we wanted to talk about each of the data points individually, we would, in general, we call our data X, but if we want to talk about each one, then we index them with the little subscripts here. So we would call the first one X1, the second one X2, the third one X3, fourth one X4, etc. So we have X5, X6, X7, X8, X9, X10. I'll just go ahead and write them all. Okay, so we have 10 data points here. So if we wanted to talk about the deviation, like the deviation of our first data value, so the deviation of x1, which is 0, this is going to be 0 minus x bar, So we need to know what x bar is, right? Let's calculate x bar. I'll just do it on my calculator here. So remember, for this, we're just adding up all the data values and then dividing by 10 because we have 10 of them. 70, 75, 86, 90, 100. So we get 628. Divide that by 10, we get 62.8. Okay. So this is 0 minus 62.8, which is negative 62.8. And notice this is not positive, right? When we're just talking about the deviation, it doesn't always come out positive. In fact, it'll be negative if your data value is below the mean, and it'll be positive if it's above the mean, because the negative kind of tells you the direction. This is kind of telling us that 0 is 62.8 below the mean. That's what the negative means here. So if we just kept doing that for each one, right, we would do 40 minus 62.8. So we get negative 22.8. X3 is 50. So we have 50 minus 62.8, which is negative 12.8. X4 is 55. 55 minus 62.8. So we get negative 7.8. X5 is 62. So we get negative 0.8. X6 is 70. Whoop. 70. So we get 7.2. So now they're positive because now the data values are higher than the mean. So we get 7.2. I'm just doing these in my head, so I apologize if I make an error here. I might not catch it since there's nobody to call me out on it. So this is what, 12.2. And we are going to need all of them. That's why I'm doing all of this in order to use the standard deviation formula. 86 minus 62.8. 23, no. 22.2. Yeah, no, sorry, it is 23.2. Um, 90 minus 62.8. So we got 27.2 here. Yeah. And then finally, 100 minus 62.8. That's going to be 37.2. So these are our deviations from the mean. We got negative 62.8 all the way down to 37.2. So these are just giving us a raw distance. This is how far apart all of our data values are from the mean. So this is fine because we have 10 data values, right? But what if we have 1,000 data values and we want to know generally how far away they are? In other words, like what's their average distance away from the mean? So that's what we want to do here. We want to look at, that's what the standard deviation is. It's basically taking the deviations and taking the average, but also a little tweak. We're not quite doing that because we also want to make sure that they're always positive. Like I said, the negatives are basically just telling us the direction. So the negative 62.8 means it's 62.8 below the mean. Negative 0.8 means it's 0.8 below the mean. We are usually just interested in the raw distance, like how far away is this from the mean, not necessarily which side it's on, whether it's below or above. So instead, we just want to make sure that they're positive. So we do something to make sure they're positive, and then we take the average. Okay. So in order to do this, we first calculate what's called the variance. The variance and the standard deviation are almost the same thing, just the standard deviation is the square root of the variance. Okay. So the variance is equal to the standard deviation squared. Yeah. Which, in other words, means the variance, the square root of the variance is the standard deviation. Okay. These are equivalent because you can just take the square root of both sides or square both sides. So if you find one, you basically have the other. You just have to do one more thing. So typically we start with the variance, and then we take the square root of it to get the standard deviation. So let's look at how to find the variance. The variance, sorry, so this would be like a definition. The variance is the average of the squares of the deviations. So squares meaning we're squaring them. So this is what we can do. So I said before we need something to make them positive. Okay, there's a few ways we could do that. Like we could take the absolute value, but that's just not usually the way that it's done. Instead, what we do is we typically take the square of it. If we square something, meaning we multiply it by itself, then it's always going to be positive, right? Because if we take a negative number and multiply it by itself, then we have a negative times a negative, so we get a positive. If we take a positive number and multiply it by itself, same thing, positive times a positive gives us a positive. So by squaring it, we make sure that the numbers are always positive. That's really all we're doing there. The reason that we do the squaring instead of the absolute value is more technical, but essentially it just eliminates the error possibility a little bit more. So yeah, we're gonna take all of these and square them, and then we're gonna find the average of them. Okay. So the notation for variance, the sample variance is s squared. So just s squared. And the population variance is the Greek letter sigma squared. Okay. So this is sigma. It's a lowercase sigma. Okay. A lowercase sigma is this letter here. And the uppercase one was the one we were using for the sum, right? This one. Let me see if I can make this into math so that you can kind of see what it looks like without just my handwriting here. Nope. Okay, let's see. There we go. Yeah, this is what it should look like. It makes it way too small. But yeah, it looks like this letter over here, the sigma. So yeah, that one's not too hard to write. The mu can look kind of like a U or an M, depending on your handwriting. So you can see this is not, whoops, that's just a standard U, right? So it didn't pick that one up. It's easier to see in the book because they're typing it. I don't have any way to type the Greek letters. But anyway, yeah. So this is what we're using for these two here. For the standard deviation, we use the same thing, except we're just using S and sigma without the squared. Because again, the variance is just the standard deviation squared, so it's reflected here in the notation. S by itself, not squared, is the standard deviation. Sigma, not squared, is the population standard deviation. Okay, so we'll use that same notation when we talk about the standard deviation. So let's talk about how we would take these values here and find the variation with them. Okay. Well, first of all, let's just kind of come up with a formula so we can describe what we're doing. First, let's talk about the population because we do have to do something a tiny bit weird in the sample variance. Oops. Okay. Population variance, just, sorry, variance, not variation. Population variance follows directly from what it says to do here. We find the average of the squares of the deviation. So the deviations for each one are xi minus x bar, right? This is the deviation. So if we're squaring it, then we just write the exponent here. We square them. And now we want to take the average of them. So to find the average of them, we add them all together and then divide by however many there are. So our symbol for adding everything together is a capital sigma, and we want to add all of them. So we're going to start at 1 and go up to n. Remember, big N is how many numbers are in our population. And then we're going to divide by n here. And actually, we're talking about the population. So we're not using x bar, we're using mu. Because we're using the population average in that case. So this is the population variance. And if you wanted to talk about the population standard deviation then, by the way, so this would be sigma squared using our notation. So the population standard deviation, if we look back up here, like I said, the standard deviation is just the square root of the variance. So we just take the square root of all of this. Okay. We're still doing the population, so we're still using mu. Write that a little better. Okay. So it looks kind of complicated, but if you just take it step by step, it's not so bad. Like first you find the deviations, then you're squaring them, then you add them together, then you divide. Okay. If you're confused about the order, remember your order of operations, your PEMDAS. First you do what's in the parentheses, then you do the exponent, and then we do the addition. And you might be wondering, why do we do division last? It's really because with fractions, it's like a type of grouping. So it's kind of like we have an implied bracket here where we do everything on the top first and then we worry about the bottom. Like we simplify the top, simplify the bottom, then we do the division. That's always the case with fractions. But at least for the top, you can just think about the order of operations directly. parentheses, then exponents, then addition. So we already did the parentheses for our data up there. But before we talk about that, I do need to talk about the sample variation, because it has a slight difference, which is kind of weird. Sorry, variance. I keep saying variation, but they are sometimes used interchangeably, but we should be using variance. So when we are using a sample, we don't actually divide by the we don't divide by n, okay, which is kind of weird. So let's look first at what we let's just look at the formula first. I do want to mention something. Hang on. The book is using the letter F in the standard, not the standard deviation, but the sample formulas. So I just wanted to mention, well, it's using them. Sorry, it's giving like either option. It's using like this letter F to represent your frequency. So it's basically like if you have like repeated values, it's just saying you don't have to do the deviation more than once, because they're going to have the same deviation if they're the same value. You could just like do it once and multiply by 2 if you have 2 of them. But you don't really need to worry about that. You can just ignore the F and just use these formulas. It just kind of makes it simpler. So anyway, with the sample variance, most of this stays the same. Sorry. Whoops, I had one error up here. This should have been a big N, right? Because we're talking about the population. So with the sample variance, our notation changes a little. We're using little n because little n is how many things we have in the sample. We're still squaring everything. We're using x bar now because we're using the sample average. But one difference is that instead of dividing by n, we're going to divide by n minus 1. Okay, sorry, this shouldn't have a square root either. There we go. So this is the sample variance. So why do we divide by n minus 1? It's not an easy question to answer. There's something in statistics called bias, which means if we're using something to estimate, if we're using a sample statistic to estimate a population parameter, is it like a good estimator or is it a biased estimator? Meaning that it always comes out a little bit off of where it should be. It turns out if you divide by just n, it is a biased estimator. We typically want things to be unbiased though. Bias is typically something we're avoiding in statistics. So by dividing by n minus 1, it makes it unbiased. Okay, so that's not really something we get into with this class. It's something that you would get into more with like a calculus-based statistics class. But that's why n minus 1 is coming here. It's basically just gives us a better estimation of the population variance. Okay. So we're just dividing by n minus 1 instead. And our letter we're going to use to represent this is sigma. It's, sorry, I'm like, I used the wrong letter. Sorry, this one should be sigma. Yeah. Did I say it right up here? Yeah. Okay. So with the population, we're using the Greek letter. Population variance sigma squared. Population standard deviation is just sigma. Because this one is the square of this one. Yeah. Sample variance is little s squared. And then the sample standard deviation, whoa, sorry. Don't know why that happened. The sample standard deviation is the same thing, but we're going to take the square root of it. Okay. So we're going to add them up to take the average, all that. Still dividing by n minus 1. So we literally do the same thing, except we just take the square root at the end. Okay. So this one is represented by the letter S. Okay, so let's do an example of this finally. We have our data up here, our deviations. Let's go ahead and take, well here, let's write out what we're going to do first. Let's take our data value, our data set. Let me copy and paste them. Okay, so we got our data set here. So if we want to find the variance, and remember this is a sample variance because this is only a sample, right? The sample variance, which is s squared, is going to be just writing everything out based on the formula. We take the deviation, so that's 0 minus 62.8, square it, and then we're adding the next deviation squared, 40 minus 62.8, whoops, squared, plus 50 minus 62.8 squared. Okay. And we're just doing this for all of them until the last one, which is 100 minus 62.8 squared. We're taking this whole thing and we're dividing it by 10 minus 1, so 9, right? Not exactly how we had it written here, but I had to go on the second line, so I didn't write it as a fraction, but the division, same thing. So we're squaring each of the deviations, we're adding them together, then we're going to divide by 9, which is 1 less than however many we have, so n minus 1. So that's how we're finding the sample variance. Of course, we already have all of these numbers, right? We have them from up here. So we would take all of these, square them, and add them together. And then we're going to divide by 9 at the end. So let's see here. Negative 62.8 squared. Remember, square means multiply by itself. That's going to be 3,943.84. And then we add the next one squared, which is 22.8. So 519.84. And we just keep doing this for all of them. Okay, the last one is 100 minus 62.8. 37.2 times 37.2. So we have 1383.84 divided by 9. Okay. So it's a big calculation. I won't do it here. I'll do it I'll show you how to do it in Excel in 1 second here. So actually, let's just go ahead and do that in Excel. So you could just do this in a calculator by hand. That's fine. Or I'll just show you how to do it in Excel, since that's probably something that everybody has. Or something similar, like if you have Google Sheets or something like that, that would work just as well. Let's go ahead and type our data in here. So I'll just type in our data. We got 0, 40. You can do it horizontally or vertically. It doesn't matter. 50, 55, 62. Yeah, and like I said, you can do this in a calculator. I'm sure there's plenty of online calculators that can handle this. This is just something that I think might be more accessible to everybody. 86, 90, 100. So these are our data values here. So if we wanted to find the standard deviation or the variance, we would just go over here. You can go to more functions and then statistical. And we are finding the sample variance, right? So var p is for the population variance. var.s is for the sample variance. You can see the description here estimates variance based on a sample. And this one says it calculates variance based on the entire population. So we're going to use the sample variance. And then you can just go ahead and highlight the data that you want to use. And it spits out 839.0667. So if we wanted the standard deviation of that, we could either just come to our calculator now and type in square root of 839.0667, and it should be 28.97. But we can also just do it in Excel also. Okay, so that's the variance. So the standard deviation, we should do the same thing here. This function right here, the dev squared, this will give you just the sum of the squares of the deviations without dividing by anything. So it's one of the things we calculate like along the way, but we can just do the standard deviation. So we want standard deviation S again, because we're using the sample. I don't know what A is. Oh, A lets you type in like actual words too. So we wouldn't need anything like that. But we can do that. We can highlight the data, and then it spits out the 28.96 there, right? So that's the standard deviation. So this is the easiest way to do it, because you can see like doing it by hand here is extremely tedious. And hardly anybody would actually calculate this by hand more than like 1 or 2 times to make sure they can do it. Usually you're doing it in a computer, whether it's in Excel or in a statistical programming language. I think for social sciences, you typically would use SPSS, and it's probably pretty easy to do in that. I'm not super familiar with that. I use something called R, which I actually don't have downloaded on this computer, but I will download it at some point so I can show you how to do some calculations in it. And I am going to look into SPSS and see if I can show you how to do stuff in that one as well. But yeah, so that's how we would find them. So we found the sample variance was 839. And we're approximating here because we're rounding off. Excel is automatically rounding it a bit. 0.0667. And then S, which is the sample standard deviation, is the square root of this, which is about, so the squiggly equal sign, I guess I should have mentioned, it means approximately equal. So that's why I'm using that. 28 0.9. Let's just say 7. Okay. So this tells us on average our data is about 28.97 points away from the mean. So if we look back at it, our mean was 62.8. So we're saying that if we averaged out how far everything is away, it's about 28.97 away. So the idea here is we square it in order to make it positive, and then at the end we take the square root to kind of undo that squaring. Okay. So the variance is always going to be, well, not always, but oftentimes it's going to be a pretty big number, depending on your data and your standard deviation. So the variance is, like for our purposes, it's kind of useless on its own. It doesn't really tell us much. We're much more interested in the standard deviation. It's just that typically if you're doing it by hand, you would calculate the variance first and then take the square root to get the standard deviation. So that's the only reason I have it here. If you're just like in Excel, then just use the standard deviation formula. Okay. So yeah, we take the square root at the end to undo the fact that we were squaring them. We squared them to make them positive, and then other than that, we're just taking the average. So in a sense, this is the average distance of each data value to the mean. Okay. All right. I think that's pretty much everything. We can do one more example though. You really just need to be confident in doing this in Excel more than anything. So I don't know. I don't really have any like data sets on hand here, but let's use one from the book, I guess. Or here, let's just use like, what if we just use like the first 10 digits? Because it's kind of an easy set to think about what should happen. Let's think about the numbers 1 through 10. Okay. These are perfectly spaced out, right? They're all exactly 1 unit away from each other. Actually, let's throw 0 in there as well. So what's the mean of this data set? Well, since we're in Excel, I might as well show you how to do that here too, right? The mean, you can just look for the word average here. I don't think it actually, it doesn't actually use mean. It just uses average to mean the mean. And then you can highlight it and it'll give you 5, right? So that's what the mean is. Because this data is perfectly spaced out, the median will be the exact same thing. Oops. So you can go look for the median function, highlight it, press OK, it gives you 5. Not to get too sidetracked here, but we could also look for like percentiles or quartiles using these functions. Let me see if, I don't think I've ever actually done that. So let me see if they just have one of the functions. Percentile. So this returns the kth percentile of values in a range. So inclusive means that you're using the upper and lower bounds as part of the range. Exclusive means you're not. Do they have, and they have quartile, same thing. So if we wanted quartile, we could use inclusive, and we could use the third quartile. We'll get, and this tells us the third quartile, you can see right here, is 7.5. If we want the first quartile, You can see right here it's 2.5. Second one is 5. Fourth one is 10. So this tells you, so you can pretty much do everything we've done in section 2 in chapter 2 in Excel. If you instead wanted like a percentile, like the 40th percentile, I think that was one of the questions on, or it's going to be one of the questions on the next homework. So notice it says K should be between 0 and 1. So if you want the 40th percentile, you should type in 0.4. Okay. If you want the 45th percentile, you should type in 0.45. Our data is just 1 through 10, so it's just basically like the same number. So nothing too interesting is happening here. But that's how you would type it in. 10% you would type in as 0.1. So anyway, let's find the standard deviation. We're always doing it with the sample. So you can see here it is 3.316. So that's kind of interesting. Well, why would that be the case? Well, the mean is 5, right? So 4 is 1 away, 3 is 2 away, 2 is 3 away, 1 is 4 away, 0 is 5 away, right? And on the other side, 6 is 1 away, 7 is 2 away, 8 is 3 away, 9 is 4 away, 10 is 5 away, and then 5 itself is 0 away. So essentially, we're just taking the average of all of those, right? We're doing 5 plus 4 plus 3 plus 2 plus 1 plus 0 plus 1 plus 2 plus 3 plus 4 plus 5. These are the distances away. So we get whatever this is. If you want to actually calculate the formula, you just put an equal sign in front of it, and it'll tell you it's 30. There were, how many distances was it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 distances here. So when we divide it by 11, again, just put an equal sign in front of it, we get not quite what the standard deviation is. So what is this telling us? Well, it tells us that squaring it makes a big difference. What I essentially just calculated here was the absolute value instead of squaring it. So squaring it did make it a little bit different. Also, I didn't actually divide by n minus 1, which would have been 10. I divided by 11. So it does change our number a little bit. So this is kind of like what we might logically think we should do, is get this 2.72. But what statistics tells us is that 3.32 is actually a better estimate of the population standard deviation. Okay, so it is a little bit different, but it's still pretty close. I just wanted to show this number so that you can see this is kind of what we might expect it to be if we're just like logically thinking through it. And this one's not too far off from that. So yeah, anyway, I'm getting a little sidetracked here. I'm kind of like trying to show you like the ideas behind this. But yeah, when you're calculating the standard deviation, this is what I would recommend you do. I would just recommend coming here, typing it into Excel, and then finding the standard deviation that way. This also would be good practice for like future jobs and stuff, because lots of jobs use Excel. So it's a nice time to get familiar with it. If you're going into like a role as like a sociologist, I would expect you would maybe use something like SPSS, a statistical software. So it could probably it would be able to do like the same stuff. It's just going to be how you do it would be a little bit differently. I don't know if we'll have access to that. Hopefully, I can show you a little bit in that. If not, I'll show you at least in R, which is another statistical programming language. The only difference is R is like aimed towards like general statisticians, whereas SPSS is statistical. It's like a statistical program for the social sciences specifically. So it's more aimed for like sociologists or psychologists or just people in the social sciences. So it's more geared towards like what you would do in those fields. But we can do all of it in R too. So if I can't get my hands in SPSS or something similar, I'll show you in R because R is actually free. I don't think SPSS is. So anyway, you could just play around with this, make your own data sets, like say like some homework scores, right? Like where maybe people get points for turning it in, but then a few people didn't turn it in. So how does that change everything? And then you can look like, okay, here's the standard deviation. And then you just highlight it and see, okay, those zeros brought the standard deviation down quite a bit. If every number was 10, and notice as I'm changing these numbers, our formula knows what numbers we were using, so it's changing it based on that. If every number is 10, there's no difference between them, so the standard deviation is 0. And that's the lowest the standard deviation can be because it can't be negative. And while you're here, you can look at some other functions. These are all functions that we might come across at some point, so they're all very useful. So yeah. The standardized I'm wondering if that would give us the same thing here. Let me see. No, okay. That's something different. So never mind about that. Yeah, you can just play around with the variance formula, the standard deviation formula, mean, median. You can also look at the mode. I don't know if actually there is a mode function. Oh yeah, here it is. Whoops. So I did it in the backwards order. I highlighted the data first. Do you want to highlight the data second? So yeah. I either did it wrong or it's just telling us there is no mode because there's no repeated number here. Right. Let's see. Mode. Yeah. So that one just there wasn't a mode. Here the mode is 10 because that's the most common number, right? Here it's not repeated. There's no number that's repeated, so there was no mode. If we change this to a 1, which throws off all of our other data, and then we look for the mode, then we get 1 as the mode because that's the most repeated number. So I'm using mode single here instead of mode multi. The multi would basically be if you have like several sets of data, and the single is like because we just have this one set of data. Okay. I think that's all the things we have talked about. Quartile, percentile, like I said. You can actually calculate the skew. We talked about what skew was. We didn't actually talk about like calculating it though, so don't worry too much about that. I think that's it. I know I've kind of been rambling here. I just already had Excel pulled up. I figured I would go through and look at other things we've done. But I think that is it. So thank you guys for watching today. That is the end of chapter 2. So make sure you do the homework problems in this section because it's good to practice this stuff. Again, I don't mind if you just do them in Excel. I would try maybe at least a couple of them by hand so that you understand what's happening in the formula. Because it's good to understand the formulas so you know like why these numbers are important and where they're coming from. But yeah, next time we'll start chapter 3. So I'll see you guys then. So thank you for watching.